Alrighty, so hello and welcome. Howdy. We're here again with another question. Oh man. Let's see how quickly we could do this one. Let's see how we do. Let's see how we do. I've seen variations on this question before. So it's best time to buy and sell stock number 3. And let's see what it says. Had kind of a long break, took some time, just hung out for a bit. Watch some evangelical videos, I guess. And yeah, preachers talking about God. Best time to buy and sell stock 3. Okay. Given an array of prices where prices of I is the price of a given stock on the ith day, you find the maximum profit you can achieve. You may complete at most 2 transactions. Okay, interesting. Do not engage in multiple transactions simultaneously. You must sell the stock before you buy again. What? I don't know. This is going to be challenging, I think. I don't know if I know the answer to this one. So, okay. So, price of a given stock on the ith day, find the maximum profit you can achieve. You may complete at most 2 transactions. May not engage in multiple transactions simultaneously. You must sell the stock before you buy again. Let's see some examples. So 335,00314, output is 6. Buy on day 4, so 1, 2, 3, 4, price 0, and sell on day 6. Excuse me, you get profit of 3. Buy on day 7 and sell on day 8. Okay, so you can make 2 sales, 1 purchase and 1 sale on each per day, and you're going to make 2 purchases and 2 sales. And you're going to try to maximize your profit for those purchases and sales. So that's interesting. I think this might be easier than they're letting on here. I suspect you may have to do some kind of like, what do they call that? Like a depth first search type of thing, a recursion, or possibly dynamic programming. That's what I think they might be getting at here with this. That's probably why they called it hard. I'm like unnerved because they called it hard. But I don't think it's necessarily that hard, right? Like obviously, if you could just buy and sell on 2 different days just once, then you could just take the largest difference between 2 numbers. And then if you're going to make 2 transactions, then you want the 2 largest differences. While not taking the 2 largest differences that exclude the other days that you bought and sold. So you could find them. So I guess it is somewhat challenging in that the 2 largest differences might be connected to the same point, and then it makes me think of like the triangle, like a triangle inequality. They might be connected to the same point, so you need to use a different day for one. So that they could be. So okay, the reason why you couldn't just take the 2 largest differences is because, well, you can't use the same largest difference twice, right? Because they're not allowing that. So that's the first problem. The second problem is that, okay, well, obviously if you had like A, B, and C and D, and A not equal to B, not equal to C, not equal to D, where A and C are when you buy and B and D are when you sell. Also, what is make it more challenging too? I think they have another issue of must sell the stock before you buy again. Can engage in multiple transactions simultaneously. Okay, I see. So actually, it's not that hard. It actually makes it easier if you're not allowed to do that. So you can't. So you have to do buy sell buy sell. That's the pattern you need to perform. So really, there's some index that you have to find that if you split the array into two pieces, you find the maximum of the first index and the maximum of the second index, maximum differences. And that gives you some number, and you take the maximum of all those numbers. Obviously, you have to split the array into two arrays that both have at least two elements for it to be meaningful. If you only have three elements, they also need to be the differences actually have to be non-negative, and the differences themselves are ordered. So like, you can only compare things you bought with things that come after it in order to potentially sell them. So that's interesting. So, and this is supposed to be linear time, by the way. As you can see at the bottom, the constraint's 100,000. So I guess this is a little bit harder than I thought. I don't have an obvious answer. I guess what I'm struggling with is just understanding the question in the first place. So yeah, you have to read carefully. I think that's something we learned earlier, is that sometimes these problems, they're not as hard as you think, but if you don't read them and understand what they're saying, then they're really difficult. Could be really difficult. So day one, sell on day 5. Cannot buy on day 1, buy on day 2, and sell them later, engaging in multiple transactions. That's what they were explaining before. So it has to be day 1, day 5, and you can only do one transaction. So it could be just the outright best differences. So you could do a few different things. You could say you can't buy anything, 0. If you have the array has at least 2, then you could take all the differences from left to right. Could we do that in linear time to get those differences? I take the maximum difference. I suppose you could. Maximum difference between any two numbers. You gotta think about how you might do that if you just had one transaction. I think the way you do that is that's a maximum subarray sum, and that'll give you a maximum subarray sum, and the idea is that would actually give you the largest. That's a pretty interesting one, the maximum subarray sum problem to get the large. So in linear time, you can get the largest difference. Let me just think about that for a second. Why is that? Because largest maximum consecutive subarray sum. Oh, I think that has to be the largest consecutive sum over the differences. Consecutive subarray sum over the differences. Yeah. Not over the numbers themselves. Yeah, it's really interesting. Why that would give you, if you take the differences and then you take the maximum subarray sum over the differences, that'll actually give you the best point to buy and then sell. What's interesting about that is you can't just. Why couldn't you just take the lowest minimum and the highest maximum? Wouldn't that be the same thing? That would be better. That's a lot easier. Find the minimum, take the minimum and the maximum, take the difference between the two. Yeah. Duh, that's super easy. No, because no, the reason why you don't want to do it that way is because the minimum might not come before the maximum. Oh, it's not that easy. No. Oh, that's a very subtle thing. Yeah. Right, I see. Okay, that's why you would want to use the subarray sum, consecutive subarray sum of the differences. That is super clever, super interesting. Okay, well anyway, so yeah, I've seen this problem like a million times, but you do that if there's only one transaction you can have. Take the maximum subarray sum of the differences, and the differences are just difference from one stock to the next, one day to the next. What you can do once you've already tried that, right? So you've already, so you have more than at least two elements. Take the maximum subarray sum, which I can code that up. That's not too bad. Take over the differences. Then that gives you some maximum number if you just have one transaction for the whole thing, right? Now you might want to have two transactions, so now you can split the array into two pieces and perform your maximum subarray sum, right? Two pieces where you have at least two elements, perform maximum subarray sum on the left side and the right side, and you can compare those. Now the problem with that though is you could do that in quadratic time, right? And you would just compare adding the two, to get the maximum of the two numbers added together. Part of the issue there is, I don't know if it's that simple or that easy. If you can get the maximum subarray sum on the left side and the right side, can you get them simultaneously? I'm actually not too sure. I mean, you could do the maximum subarray sum from left to right, and actually like decompose the algorithm such that you have the maximum subarray sum that ends at a particular index I, and then you could also perform from right to left to give you the maximum subarray sum that ends at the same index I. So you could do left to right that starts at I and right to left that ends at I, and you could store all those values, and then you could loop over those summations. So then you could say you could do left to right to a certain index, and then right to left at sort of the I+1 index, and you add those two numbers, and so you could loop through those values. So instead of using the dynamic programming approach that doesn't save the values, you could actually save the values, do it left to right, right to left, and then you could just take a sum over the numbers, sum over the results. So you handle the 0 case, the 1 case, and the 2 case. So that's not bad at all. That's pretty interesting. Let me see, how much time do we have here? That was 13 minutes. Yeah, that wasn't too bad. That was okay, I guess. Let's see how long it takes to code it though, and let's see also if we're correct. I think that's the way to do it, but we could be wrong. So edge case, if you're less than or equal to 1, so we'll say if, and we'll call this P instead of prices because I don't know, it's typed so much. Right, don't have enough. Simple subarray, consecutive subarray sum. So start with differences, prices. So we'll have an array of integers. We'll say diffs, and it's going to be p.size, and we're going to initialize. So it's actually going to be p.size minus 1. So the differences have one less value because you're going to take the next value minus, so x of I plus 1 minus x of I, right? Which actually gives you one less number. So we're going to say for int I equals 0, I is less than p dot size, increment I, and it's going to be less than p dot size minus 1. And we're going to say p of I is equal to, or not p of diffs of I, is equal to p of I plus 1 minus p of I. Okay, so we'll say int ret equals 0. We're going to say here. So the way this works, there's a ret value, and then there's a, so actually we're going to do a couple things. So we're going to say, end this step, we'll also compute reverse subarray sum. Save both forward and backward sums at each index to separate arrays. So this should be interesting. So we could actually do them simultaneously. We could say, let's see. Now what's interesting is the reverse subarray sum. I'm actually not sure how to do that. We'll come back to that in a minute, but we're going to say, so forward sums, we'll int forward sums of size, I think it's p dot size now, because the forward sums are kind of interesting. We'll come back to that in a moment, but I think it's actually p dot size minus 1. So the way the subarray sum works is that you want to find the largest consecutive subarray sum at a particular index I, from ending at a particular index I, and to get the subarray sum over the whole ending at a particular index I, excuse me, maximum subarray sum that ends at a particular index I. So it could be any starting point from the left side, but it ends at this particular point I. And the idea is then you could just take the maximum over all of those once you're done. But we're actually going to save each of those as we calculate them. And the way that's going to work is, what you do is you say, okay, starting from the initial point, we say, if we know previously what the largest subarray sum was of the previous array, what we can do is say, okay, we want to calculate the largest array that ends at this particular index I. So we can take the previous one that's the largest so far that ends at the previous array, and we can either add the element that we're considering now, or if the element itself is larger. What is it? I think there's 3 options. You can add this element. No, excuse me. You have to end at this particular index I. So either you take the element alone, or you add it to the previous sum. And yes, that's the key. It has to include that element because it has to end there. It's the largest subarray sum that ends at that point that includes that element. So if that element is negative, we still add it, potentially, if the previous subarray sum is positive. If the previous subarray sum is negative, then we don't add it, right? We just start fresh at this new negative number. It's a very subtle thing, but so we're going to say int I equals 0, I is less than p dot size minus 1, increment I, And we're going to say, we can do n, we can do it this way, we can do n and, do something like this, just so things don't get so confusing. You could just use n everywhere. Okay. So now, what we're going to do is say forward sums of I is going to be, and we're going to have a value previous equals 0. No, and it actually includes, so it's actually going to be something like this. So forward sums of I has to be the initial difference, the first one. So diffs, maybe we just use D instead of diffs. Prefer D. It's a little bit easier. So 0 will be here initially. And we're going to say, take the previous forward sums, I minus 1. And we're going to say, either you're going to add the previous, this new value. So we'll say const auto x, or just const int x equals d of I. You're either going to add this value x, or you're going to just take x itself. And you're going to take the maximum of these two. Yeah, we'll do it this way. It's easier to write this way. So, all right, 20 minutes in. So we're either going to take either the previous sum with x or just x itself. So this is going to be at every index I. It's going to be definitely contains that element for index I. So this will ensure that at every index I we have a record of the best possible subarray sum that ends at that particular index I. And then we can take the largest over that entire sequence, and that could be one possibility. So we would say ret is equal to standard maximum of itself and forward sums of I. Right, so we can calculate that as we go. Update ret to the largest value. Now, what we want to do is we also want to calculate the subarray sum, the largest subarray sum from right to left. Now, what's tricky about this is I think we actually need to use the negation of the differences if we go right to left. Yeah, which is kind of a tricky thing. If you were to reverse the array and then calculate the maximum subarray sum, now you're buying on the right side and selling on the left side, which is why you need to negate them, because now you're trying to sell on the right side and buy on the left side. So you're actually trying to find the largest negative. So it's, yeah. So you'd actually have to, you'd have to go, if you want to go right to left, you have to negate the differences, which is really weird. That's the thing that's kind of tricky. And those sums themselves would actually be negative. Or would they be negative? They'd be, yeah, see, that's the thing I'm kind of hung up on. Like, do you get the same answer if you get the subarray sum from right to left as left to right? I don't think so. If these were strictly, see, that's the thing that's really tricky about this. I'm not actually sure. because we're using differences, it represents something else. I could be wrong. I think the maximum subarray sum from left to right is the same as right to left. I think it has to be. That's a really subtle thing. It's super subtle. Super subtle. But you can do a similar thing and have, I think you can do both. I think you can do forward and backward. And we don't need to initialize these either, because we're gonna write to them here. It's almost the same thing, but in the other direction now. So I is going to start off at n minus 1, and I is going to be greater than or equal to 0. And now we can say, same deal. You have x is d of I, and we're going to say backward sums. I think this still works, actually. I think it's okay. I think it's okay. And we're going to say, and now it's I plus 1 instead of I minus 1. So from left to right, we're looking at the thing behind us. From right to left, we're still looking at the thing behind us, which is I plus 1. Now we're going right to left, I plus 1. And this is minus 2, and this is backward sums of n minus 1 equals d of n minus 1. Okay, I think we can do the forward sums and the backward sums and do it this way. And then we can say update ret considering the potentially splitting price array into 2 pieces. Okay, now we can go for int I equals 0 to, so the split could be from, and this is only if, so here we're greater than or equal to 2. This part we only care about if, this is if actually I think if we have 3 elements, if we only have 2 elements, then the forward we only have 2 elements, n, so this is actually n minus 1. We should, oh no, yeah, it is, yeah. So if only 2, n is just 1, so then this ends up being, this actually doesn't happen if you have only 2 elements at all, this whole part. Because the difference is, if you have 2 elements, you could just set this to d of 0, right? Just thinking here. Yeah, if you have 2 elements, you could buy and sell, or not. You know, your best bet would just be to just not do anything. So we would just say, you know, d of 0 is greater than 0. Then you have d of 0 Otherwise 0. So you have 2 elements, you don't do anything. If you have 3 elements, you can do this processing and also set up the forward sums, but would you set up the backward sums with 3 elements? I is n minus 2, which would be, if you have 3 elements, it would be 2. So I think, yeah, I think you would do one thing on the backward sums, but it wouldn't, there's nothing to do. Like, there's no processing after this point. Like you would set I to I think the starting point would have to be start off at 2. Yeah, so you just wouldn't do anything. I think it's fine. I don't think we need to add this if statement here. Just return red at the end. Yeah, handling 3 would be handled here, and then anything more than 3, 4 or more is when you can actually split into 2 and 2. The forward sums would be set up properly for 2 as well. Forward sums, backward sums. I don't know actually if you do 3 and 4. Let's just write the code and see if we could do works for 3 and 4 as well. So the idea is that I starts off at the split point is where we're going to put I. I is going to start splitting at index 2. And we're going to say I is less than, you can go all the way until you have the last, so you have leave 2 elements. So n minus 2. Yeah, that index where you have 2 elements at the end, right? So those are the indices. You're going to go from one to the other, and you're going to say ret is equal to the maximum of forward sums of I plus backward sums of I plus 1. Something super simple like that in itself. And then you return ret. Let's just see if this compiles. Let's start with that. So you would go to, so you would process, you have your sums that end at I. Now what's interesting is it's actually, I actually have this wrong. It's not the, what you'd want to store is actually the best value up to I, not the ones including I. So I got this wrong. The forward sums, it's going to be, there's going to be this int t. Oh, we're going to have this int t is equal to ret. Forward sums of I is actually going to be, so we're going to say t equals standard max. It's going to be this of itself. Right? T plus x of x. Forward sums of I is going to be set to t. That's what we want. And then this is also going to be the maximum of ret and t. So this is a little bit tricky. So we want this value, and then normally this would be the normal algorithm. You'd have t and then ret value. But actually forward sums of I we want to set to, not to t. Yeah, we want to set to, really it would be what ret is at that, up to that point. Not just t. That's the tricky thing, right? So this is whatever ret is up to that point, the best so far. That's kind of subtle. It's not too subtle, but yeah, it's a tricky thing. Yeah, so this is also ret then. This is really just ret. Doesn't need to be t. This is really confusing. Sorry, confusing things here. There's two numbers that are going. One number is absolutely including that particular point. Another number is the total return, which is just the best you've seen so far up to that point. So the tricky thing though is t actually has to start off with d of 0. Yeah. Forward sums actually is the best you've seen up to that point, which could be 0 if it's negative, doesn't include anything, but it's not necessarily t. T has to include d0. Yeah, that's a subtle thing. Right, so t gets calculated as you go, and ret is the best you've seen so far of t, and then each point is going to be what ret is up to that point, and you do the same thing on the other side as well. Set t equal to d of n minus 1. Backward sums is actually going to be ret again, or we'll just say int best. Say same deal. N minus 1. And this is going to be the best that we've seen so far. And then we're going to same kind of thing over here. So we say t is equal to standard maximum of itself plus x, or just x. And then best is going to be the standard maximum of the best so far and t. And then backward sums of I is going to be equal to whatever the best is. Yeah, that's super subtle, or not super subtle, but kind of nuanced how that works. And then we're going to try to get the best of the forward sums and the backward sums added together, and yeah, that's what we return with ret. Okay, so does this compile? Let's start with that. There's some more thinking to do here, I think, before like executing the code, but oh, well, it's correct here. Okay. All right, let's try the test cases, and we'll just throw in our own test cases. Can these prices ever be negative? No. Oh, okay. That kind of makes things a lot easier. All right, how about that? Try some random things. It looks like it just so happens to work nicely for the degenerate test cases as well. So there's always at least one in there. We have 40 minutes we did it so far. Yeah, it's not too bad. Kind of want to do faster than that, but that's okay. Oh, I was saying before, yeah, we could use Python scripts to generate these other test cases. Actually, we should do that. Let me like quickly get a Python script going here. All right, you ready for this? This should be interesting. So we have Python. So we're going to vim. We're going to say combinatorics.py, or just test.py, or temp.py or something. I don't know. I have test.py, temp.py. We're going to say import iter tools. We're going to say for, I don't know, x in, excuse me, let's do iter tools as iter, or it. Python iter tools are pretty interesting. So I don't remember them offhand, the documentation, but there's something pretty nifty here you can do. We want combinations. Yeah, or is it, no, permutations. We want R length tuples, all possible orderings, no repeated elements. So Cartesian product, nested for loop. PR. So P is just going to be an iterable, and then R is going to be, we could just do P, permutations P. So iter tools, we could do import iter tools as it and do P. So it dot permutations of 1, 2, 3, and we could print, and we're going to use a list comprehension of X for or A or I or Y in X. Is that it? Yeah, I think that's it. Well, oh, I did it wrong. I did do it wrong. Yeah, for Y in X. There you go. Hey! And then we could do the same thing. See how easy that is? Talk about scripting quickly. And we can do, and we can actually make this a quick script that we don't need to write every time we want to use it, but we can just run it. We can use, so what you could do is give an input a number, and then it'll get the combinations for that number. But we could just copy paste these. So these are now usable here. Aha. Let's see that. Let's see what that looks like. Wrong answer. See, you always gotta test your code, man. Always gotta test your code, man. All right, which one's failed? Told you, that's such a good test case to try when you're dealing with sequences of things. So there's 4 somewhere in there and 1 all the way at the bottom. Let's try 1 all the way at the bottom. Oh. Okay, 1, 2, 3, 4, 5, 6, 7. 7 from the bottom. Which test case is that? So I'm saying, man, you gotta test your code. We also probably close this. So 7 from the bottom. 1, 2, 3, 4, 5, 6, 7. It's this one. Did I copy paste this correctly? I did. What was I saying? So my butt. What I wanted to do, what I was thinking was, I have to check time. I do have to get going at some point here. All right. Right. What was I doing? So, what? What happened to my failing test case? Which one is it? Got this. Oh no. Can I move this upwards? This. Make this larger. Hold on. How do I how do I make this part bigger at the bottom here? I want to make this console larger so I could see more than just how do I put this part higher? I can't make this bigger. I just noticed that you can't do that. Have to copy paste the output something else to see it. It's kind of annoying. Okay, so which one is wrong? One, 2, 3, 4, 5, 6, 7, 8. Is 8 towards the bottom? There's a 2, a 1, and a 1 and a 2. 2, 1, 1, 2. 2, 1, 1, 2. There it is. And it's the first one there. It's this one. So that's 1, 2, 3, 4, 5, 6, 7, 8. Ah, it's the 8th one upwards. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Didn't we just try this one? This should be 2. Oops. Okay, let's try that. Let's see. Let's see. Okay, so we should get 1 plus 1 gives us 2, but we got only a 1. But we could add more test cases here too if we wanted to. But the problem is you have I is 2, forward sums of I. Oh, this should be 1, by the way, not 2. That might be the problem. And zero, 1. Forward sums should be 1. Plus backward sums, which is 0, 1, 2. N in this case is 4 minus 1 is 3. So N is 3, or yeah, N is 3. And this should be N minus 1 then. N is 3. So I think that might be the problem. There we go. Okay, let's go back to our test cases. So I think I have the right idea. It's just implemented it slightly incorrectly because that N I used, that'll trip you up. If you try to redefine N, and so it has sort of different meaning almost. All right, that's probably correct. Probably. I could be wrong, but like that's a lot of confidence. There we go. Okay, nice, 80%. So that could have been faster. I could have programmed it faster, and the code itself could have been faster, but 50 minutes is not too bad. That's okay. You know, it's not great, but it's not bad either. Used a little bit more memory. I don't know, we can run this a few more times and see. Could remove the max values here, or the max, yeah, functions here, and use something else. So I guess you could say s t plus x. Say if s is less than x, then set t equal to, well, you could do this. I mean, you could say t equals t plus x, and let's see if t is less than x, then set t equal to x. You could do it that way. And the same thing here. You could just say if r is less than t, set red equal to t. I think that also should work. Let's try that. Should be slightly faster, I think. Slightly slower. That's interesting. Really? I think it's kind of random how fast it goes. Yeah, sometimes it's a little bit faster, sometimes it's slower. I don't think these max values really matter that much, actually. Think about it. I think it's cleaner to keep them in there. I think we'll just keep them in there. I think it's cleaner. Oh, also the S. Actually, that was my mistake. Hold on. Oh, no, we did remove that. No, we're fine. Yeah, let's go back. There might be a faster way to do this, a cleaner way, by the way. Obviously, I did this kind of quickly. There's probably a cleaner way to do this also. What's interesting would be, can you do left to right and right to left together? I'm wondering if you could like combine these things in such a way where you don't need to use any memory, any extra memory. I don't know it though. I think I'm gonna get going though. Oh no. Yeah, that's okay. That's okay. I'm gonna go meet with some folks soon, some folks shortly. I think if there's anything else I want to look at here before we go. I mean, that's good. That's fine. There may be a better way to do this though. There may be a better way. Forwards, backwards. I think you need to define the differences. Problem with this is like the forward sums, the backward sums, you kind of need to consider them the way that I've set this up. You may be able to perform this ret value here and compare it, instead of saving the best backward sums as you go, you can actually take these, yeah, you can, I think one idea is to actually also, that's interesting, is n minus 2. Oh, I see. Okay. Yeah, so you can actually perform this calculation here and not store backward sums. So you can do actually, that's interesting. Backward sums never goes down to we never need it beyond we can do I equals 1 here, greater than or equal to 1. I think we get the same answer. That's interesting. Oh, it's a little bit faster. Look at that. Huh. One little change. We could also say, we could do this here. Comment out this part. Comment out this part. Okay, so instead of setting up the backward sums, we could just do best. So I plus 1 is I, so this is backwards of I, so we subtract 1 from both of these, so we could do I minus 1 plus best. Something like this. Does that compile? Oh, wow, whoa. Looks like it's still correct. I mean, maybe? Hey, there you go. Oh, there you go. Almost 100%. Oh, nice. So we can get rid of the backward sums altogether. There you go. How about that? How's that for efficient? How is that for efficient? So now I don't think there's a simple way of, I don't know if we can do this in a way where we don't use as much memory. You could rewrite the prices array into this vector p, right? You can write the differences, and then you could write over that array. I guess you couldn't rewrite the forward sums. That wouldn't work. You kind of need to store this in something else. So I think there might be a way to do this. It's also interesting. This is like barely faster to make it this way or that way. Don't really use much more memory either. I don't know. Save a little bit of memory by doing this. Yeah, it's not that much faster. It's okay. It's okay. Excuse me. I'm wondering if you can combine these two loops in some way so that you can calculate both of these simultaneously. I don't think so though. Like maybe you can somehow go right to left and then calculate the left to right with the things that are already there. I don't know. I don't know, man. I don't know. I don't have a solid idea. It's pretty good though. It's okay. A couple passes. How many times we passed through? 1, 2, 3 times. A few times we run through it. That's okay. I think it's good enough. There's probably some way to optimize the memory. There's probably some way to optimize the memory that I'm missing. But let me go because I'm going to leave soon to, actually, I don't know. I think I'm going 15 minutes or so. But yeah, I think it's okay what I did. I think it's okay. Yeah. Maybe we'll take a couple minutes. We'll look at the discussion then. We got 99% for speed, but we are missing. There's probably some way to combine these pieces so that we don't need to use the forward sums array. Oh, no. Oh, my mistake. I forgot to eliminate that, allocating that space. I was wondering, I was like, how come it didn't do anything with our memory? Oh, I didn't really do anything, didn't do anything with our memory. Okay. What? Didn't do anything to our memory. Oh man. We allocated 1, 2, 3. I know we can reduce one of these things, these allocations. We could rewrite the P into the differences. We could do that. I know we could do that. And then use P instead of D. Could try that just to see how far it goes. I don't know, that's a destructive approach, but we're trying to maximize memory. So you go right to left. So now you would say So you want to go backwards now. You want to go the other direction. You go n minus 1, I is greater than or equal to n, or 0. Decrement I. So now if you go the other direction, you could say p of I is equal to p of I plus 1 minus what's currently there. It's actually going to be, we want to actually write these into oh yeah, okay, that's interesting. N minus 2. So yeah, so this is going to go into p of n minus 2. Yeah, that's interesting. Yes, this is going to be written all the way down to n equals 0, and it actually will be n minus, no, n minus 2, because, yeah, okay, like this. So you could set p, you could overwrite p and then use p instead of d. Ah, there you go. And we're going to just overwrite everything, huh? This saves a bit of memory. I don't know if you could do better than this, though. I don't know. Maybe you could. I just don't know about it. We're going to keep all the other parts of it, the other comments, because it's not really the best way to do it, realistically. You don't want to be deleting your array every time you want to run this routine. Destroy your array every time. Seems kind of excessive. Everywhere you see a D, you can rewrite that with a P. Okay. How do we go here? How does this work? And we have an hour. Okay. I should probably go. Oh no. Uh-oh. Uh-oh. They're all wrong. No. Uh-huh. Oh no, but there's a problem with this approach to rewrite P, because we could still go left to right. Yeah, there's a problem because we're setting P of I plus 1 minus P. Oh, I did it wrong. Actually, yeah, I did this wrong. This is wrong. I think this is still correct. Okay, interesting. Let's go for it. That hardly saves any memory. It's like no memory is saved. It's like nothing. Okay. What? Like a tiny bit of memory. Why does this problem take so much memory? Where's all this memory coming from? What's the deal? What is the deal? What? What? I have a whole 100,000 ints that we're not using now, and somehow it's still a lot of memory. That's so weird. I don't know, man. I don't know why it's using so much memory. Yeah, I had it right the first time. Okay, well, huh. I mean, it's relatively fast. It's not crazy fast. It's using a little bit more memory than I would expect. I mean, it's okay. I kind of do want to check out the discussion now, though. Just a quick look to see. DP, ON, oh really? Is it best solution? K transactions, easiest to improve, O of N, O of 1. Oh no. Did I make a mistake? Simple, inspired, best solution with single number 2. Only have 0 money at first. 4 variables determine interested ceilings. We've just bought 1 stock, sold 1 stock, second stock, sold second stock. Maximum, if we've just works well, I have to say the logic is simple, then notice in single number 2. Huh. I think I've solved that one also, by the way. Hours to understand this. Share my understanding. 1 buy, 1 sell, 2 buy, 2 sell, 1 buy, 2 buy. Oh boy. 2 buy, 2 sell. Similar to buy and sell stock 1, only 1 transaction allowed. Keep the lowest price. Once that price exceeds the lowest price, we record the difference. 1 buy, keeps track of the lowest price, biggest profit we could get. How to handle 2 buys. Bought and sold $100. You want to purchase stock, which $300. How would you do this? Calculate 2 buy. We just minimize the cost again. As much profit as possible. Oh man, that's confusing. So apparently you can do this without using fancy. What was I just saying? Fancy consecutive subarray sums. I mean, I wouldn't know how to do that offhand, but yeah, apparently you can do. So the problem with the 1 buy and the 2 buy is hold release. Okay, I guess you could do it that way. I guess it's not impossible to think your way around that. I thought maybe there's a way to do that, but I was like, it's like too much thinking. Trying to figure all that out. Yeah, 1 buy. You just have to make sure the thing you look at afterwards, after the minimum you've seen. Excuse me. Oh, I see. So for 1 buy, I guess what you do is you just make sure you update the best possible and the best minimum and the best maximum all at the same time. You don't really need to check the best maximum. You really just need the best minimum. So the best minimum you've seen so far, check that against every value. And that guarantees the value you're looking at is to the right of the minimum. Because you saw the minimum. I see. So you could do a similar thing where you have a minimum, best minimum, take the difference between the maximum, and then also you could take another best to minimum, a second best to minimum after you've sold the first stock. Tricky thing about that is you just have to consider, like, I guess you could finagle things where, like, you would have to consider both cases where if you didn't buy and sell the first stock, and if you did, like what the minimum would be if you did buy and sell, the next minimum is, and then if you and then also figure out like what you would do if you bought and sold, and then what it would be if you didn't buy and sell the second one. So that's probably what this hold and release is going on here. So yeah, it would take me some time to think about it for a while, but we're gonna. That's interesting. So, I mean, I don't know. I like my solution. I think my solution's like kind of straightforward, simple to understand, simple to implement, but I guess not that simple. Maybe it's a little more complicated than it should be. So let me go. Thank you for watching. Talk to you soon. I should definitely get going though. Yeah, it's interesting. It's fun. Yeah, it's oh, there's also a DP recursive formula as well that someone has. Let me just see. Huh. I'm just looking. Hold on a second. Oh, he did one for O of Kn and O of N. Oh, that's interesting. So he used a DP solution that another guy used a DP solution that he like squished down. Interesting. Huh. Well, I didn't get the optimal solution on that one. That was a really interesting question. I'll have to come back to that. Take a look at it again. But yeah, I'm gonna go. So yeah, thank you for watching. Take care. Talk to you soon. Have a good rest of your day.